So to get started in section 5.3, I have to understand one concept that you may or may not understand, and that's the concept of a zero of a polynomial. A zero of a polynomial is any number that gives a zero when the polynomial is evaluated at that number. For example, I'll just make up a polynomial, f of x equals x squared minus 4. I claim that x equals 2 is a zero of this polynomial, and x equal to 3 is not a zero. Specifically, x equals 2 is a zero because if I find f of 2, if I plug that number in for the x, I get f of 2 is 2 squared minus 4. F of 2 is 4 minus 4, which is 0. So 2 is a 0 because when I plug it in, I get 0 when the polynomial is evaluated at 2. 3 is not a 0 because if I do f of 3, I get 3 squared minus 4, which is 9 minus 4, which is 5. So a 0 is any number when you evaluate the function at that number that gives you 0. Zeros don't have to be real numbers. This 0 of x equal 2 is a real number, but if I made up a new function, how about something like g of x equals x squared plus 9, I claim x equal to 3 is not a 0, but x equal to 3i is a 0. X equals 3 is not a 0 because when I plug it in, I would go g of 3 equals to 3 squared plus 9, and that gives me g of 3 equals 9 plus 9, which is 18. So x equal to 3 is not a 0, but x equal to 3i is a 0, because if I do g of 3i, I'd get g of 3i equals to 3i squared plus 9. That's going to give me g of 3i equals 3i times 3i plus 9. That will give me g of 3i equals 9i squared plus 9, because to multiply these 3i's times 3i's, you multiply the 3's together and the i's together. And because I squared is negative 1, I can say g of 3i is 9 times negative 1 plus 9. This is going to give me g of 3i equals negative 9 plus 9, which is 0. So a 0 of a polynomial, it could be a real number, it could be an imaginary number. It's just any number that you evaluate the polynomial at for x that gives you a 0. There are a couple of things about zeros that we should be aware of. One of it is that zeros that are real numbers are x-intercepts on the graph of a function. The first example that I scribbled together, f of x equals x squared minus 4, I got x equals 2 was a 0 and x equals 3 wasn't a 0. That means because x equals 2 is a real number and it's a 0, if I graph that function x squared minus 4, I'm going to get an x-intercept at x equal to 2, and that's the x-intercept at x equal to 2, and that's a 0 of x equal to 2. The other x-intercept at x equal negative 2 is also going to be a 0. This polynomial, x equal 2 is a 0 because it's an x-intercept, and x equal negative 2 is also a 0 because it's another x-intercept. But I need to know that if zeros that are real numbers are x-intercepts on the graph. Zeros that have i's can't be x-intercepts. But they do come in pairs. So the function that I made up, this g of x equals to x squared plus 9, and I said that x equals 3i is a 0. If I graphed the function, it's not going to cross the x-axis at anything related to a 3 because 3i is not going to show up on this graph. If I graph the function y equals x squared plus 9, I think I have a window that's going to make this fine. If I look at the graph, it doesn't cross the x-axis at 3i because 3i is not even on the x-axis. Imaginary numbers don't show up on a graph. So it's not going to have x-intercepts at the 0, but the zeros are going to come in pairs. If 3i is a 0, then the pair of it, which is x equals negative 3i, is also a 0. Real zeros don't come in pairs. The fact that x equals 2 was an x-intercept for this didn't guarantee me that x equal negative 2 would be an x-intercept. It could happen, but it doesn't have to happen. Real zeros don't come in pairs, usually. So these usually don't come in pairs. They can come in pairs, but it's not a guarantee. Zeros that have i's absolutely come in pairs, which means if the positive with an I is a 0, the negative with an I is also a 0. So for this problem right here, the negative 3i is guaranteed to be a 0 because if you plug in negative 3i for x, you get negative 3i squared plus 9, which is negative 3i times negative 3i plus 9, which is 9i squared plus 9, which is 9 times negative 1 plus 9, which is 0. So real quick rundown of what I've done. A 0 is any number, real or imaginary, that if you plug it into the polynomial, you get 0. Zeros that don't have i's show up on the graph as x-intercepts. Zeros that do have i's don't show up on the graph as an x-intercept, but they come in pairs. The only other thing that we really need before we get started is the number of zeros that a polynomial has. And every polynomial has as many zeros as its highest exponent. The two functions that I made up, f of x equals to x squared minus 4 g of x equal to x squared plus 9, their highest exponent is 2. So this is going to have two zeros. They're actually going to be positive and negative 2. This, its highest exponent is 2. It's going to have two zeros. They're actually 3 and negative 3i. If I made up some horrendous function like 8x to the 4th plus 2x cubed minus 3x plus 17, I may not be able to find them, but this function will have four zeros because its highest exponent is a 4. I think that's enough. I could probably say more, but I think we're probably at a good enough point now where we can get started. So I'm going to go ahead and just jump into the first 12 problems and see where it takes us. So the first 12 problems want us to create a function with lead coefficient 1, which means there's not a number in front of the first term other than an implied 1, that satisfies the conditions that are given. And in problem 2, I'm creating a function with degree 2, which means my function is going to have an x squared to get a degree 2. It's going to have lead coefficient 1, so there's either going to be no number in front of the x squared, or I'm going to write a 1. That has zeros of 4i and negative 4i. So let me try to create this function. My answer for problem 2 is going to be something I'm going to write in function notation. So I'm going to write it f of x equals, and then the first term is going to be a 1x squared. Specifically, it has to have degree 2, so the highest exponent needs to be 2, and there needs to be a 1 or nothing written in front of the x squared that implies a 1. So my answer is going to be some function in the form f of x equals to x squared, and then there's going to be some stuff after the x squared to force it to have these zeros. Super easy to create this function. I want to have two zeros, so they're going to be x equal to 4i and x equal to negative 4i. So what I'm going to do to get my zeros is I'm going to take whichever zero I want and set it equal to x, and then I'm going to set that equal to 0. So for the x equal to 4i, I'm going to minus 4i from both sides and get x minus 4i equal to 0. For the x equal to minus 4i, which is the second zero, I'm going to add 4i to both sides and get x plus 4i equal to 0. And now I'm going to create my function by multiplying the left-hand sides of each of these equations together. So my function is going to be f of x equals x minus 4i times x plus 4i. I'm going to FOIL this. First are going to be x times x, which will be x squared. Outers will be x times 4i. I'm going to write that as plus 4i times x. Inners are going to be minus 4i times x. I'm going to write that as minus 4i x. And my lasts are going to be minus 4i times positive 4i. That's going to be a minus 16i squared. The outers and the inners, because these are conjugates, cancel. And so I'm left with f of x equals x squared, and then minus 16i squared, but I squared is equal to negative 1, so it's going to be x squared minus 16 times negative 1. That minus 16 times negative 1 I'm going to write as a plus 16. I claim my answer is f of x equals x squared plus 16. To check, it should be that f of 4i equals to 0, and f of negative 4i has to equal to 0. F of 4i is going to be 4i squared plus 16. I can do this on my calculator if I put my calculator in the right mode. So let me do that real quickly. I'm going to hit the mode button on my calculator, and I'm going to make sure that it's in A plus BI mode. So I have my calculator, I hit the mode button, which is right next to the second key. I went down all the way to the real A plus BI r e to the theta I and changed it to A plus BI. Now my calculator is going to handle i's just fine. So let me quit out of this and let me show you that 4i squared plus 16 is equal to 0 by going parentheses 4 and then second and the decimal key for the I, then parentheses squared plus 16. Now my calculator is going to do 4i squared plus 16, and it gives me 0. Similarly, I should show you that f of negative 4i equal to 0 by doing negative 4i squared plus 16 and show that it equals to 0. I'll do that real quickly. I'll go parentheses, negative 4 second and decimal for the I squared plus 16, and you get 0. So I've checked my answer. You can check all of the answers between problems 1 through 12 on your calculator by just taking whatever number you're taking the zeros that are given, plugging them into your polynomial, and making sure that you get 0 back out for an answer. And we'll move on to number 3 and 4, which is going to be harder because now my answer has to have a polynomial with degree 3 with a 1 in front of the first term. And number 4, my answer is going to be of the form f of x equals, and then I'm going to have an x cubed and some stuff after the x cubed. And how do I figure out what goes after it? Well, I work with the zeros. So this part right here, the fact that I'm going to have a degree 3 tells me my answer needs to have an exponent of 3, and the instructions said a lead coefficient of 1, so there's not a number in front of the x squared. I have 3 zeros. I should do the i's first. So the zeros need to be x equal to 3i, x equal to negative 3i, and x equal to negative 5. Just like I did in problem 2, I'm going to set each of these equal to 0. For this one, I'm going to minus 3i from both sides and get x minus 3i equal to 0. That's going to be one of the factors of my answer. The middle one, I'm going to plus 3i and get x plus 3i equals to 0. And the last one, I'm going to plus 5 and plus 5. I'm going to get x plus 5 equal to 0. These are going to be the factors of my answer. So my polynomial, f of x, is going to be equal to x minus 3i times x plus 3i times x plus 5. I'm going to start off by foiling these. And you did that when you did problem 1, but I didn't do that. So let me my firsts are going to be x times x. That's going to be x squared. My outers are going to be x times 3i. That's going to be plus a 3xi. My inners are going to be minus 3i times x. That's a minus 3xi. And my lasts are going to be minus 3i times positive 3i. That's minus 9i squared. And I still haven't dealt with the x plus 5. Inside the parentheses, my first parentheses, the 3xi's cancel. And since I squared is negative 1, I really have minus 9 times minus 1, and that's going to be a positive 9. So on my next line, I'm going to do two things. I'm going to cancel the outers and the inners, and I'm going to write positive 9 because minus 9i squared is minus 9 times negative 1, which is positive 9. And then I'll deal with the plus x plus 5. I need to FOIL again, and that's actually going to take me to my answer. So my firsts are going to be x squared times x, which is this x cubed. My outers are x squared times 5, which is plus 5x squared. My inners are 9 times x, which is plus 9x. And my last are plus 9 times 5, which is plus 45. So my answer should be f of x equals to x cubed plus 5x squared plus 9x plus 45. If I want to, I could check each individual number. It's optional, but I should be able to do f of 3i, which is going to be 3i cubed plus 5 times 3i squared plus 9 times 3i plus 45, and that should equal to 0. I'll do that on my calculator. I don't care to do that by hand. You don't have to check, but it's easy to check. So to check this, I'm going to go parentheses 3i up arrow cubed plus 5 times parentheses 3i squared plus 9 times 3i plus 45, and it better equal to 0, which it does. I could also check negative 3i, and I could also check negative 5. Let me just show you that negative 5 also works. And I'm not going to check them all. The checking part that I'm doing here in purple is completely optional. But you should be able to take every 0, plug it into your answer, and it should give you 0 back. So let me just show you that negative 5 actually works as well by going parentheses negative 5 up arrow cubed plus 5 times negative 5 squared plus 9 times negative 5 plus 45, and that also equals 0. Similarly, if I did negative 3i the same way, it also gets 0. So done with number 4, so give 3 a go. 5 and 6 are... I probably should have re-recorded the whole video. This is my 3rd or 4th fix of a blurry image. So apologize for that, but I don't feel motivated to do the whole video over. I'm going to do your problem 5. It's a little bit trickier than my problem 3 because it has a trick in it that we haven't got to yet. So my problem 5, I'm supposed to create a 3rd degree polynomial. So I know that my answer to problem 5 is going to have an f of x equal to x cubed. In the instructions, I know I'm supposed to have a 1 in front of the x cubed. And it gives me only 2 zeros. I know that a 3rd degree polynomial needs to have 3 zeros. It gives me the 0 of x equal to 2, x equal to 3i. But to create a 3rd degree polynomial, it needs to have 3 zeros. I need to have 3 zeros. And the trick is remembering that zeros that have i's come in pairs. So if x equals 3i is a 0, x equal to negative 3i also has to be a 0. So to get a 3rd degree polynomial, I need 3 zeros. These are my 3 zeros. For this 0, I'm going to get a factor of x minus 2. For the middle 0, I'm going to get a factor of x minus 3i. And for the last 0, I'm going to get a factor of x plus 3i. To create my function, I can multiply these factors in any order. It's a lot better if you do the i's first. So to create my function, I'm going to multiply the 3 factors, the 2 from the zeros that were implied, the 3rd from the 0 that I created because i's come in pairs, and I'll multiply them together. For the first stage, I'm going to FOIL these. So I'm going to do first are x times x, which are x squared. Outers are x times 3i, which I'm going to write plus 3xi. Inners are negative 3i times x, which is minus 3xi. And last are minus 3i times positive 3i. That's minus 9i squared. When I do this foiling, the outers and the inners cancel, and the minus 9i squared turns into a positive 9 because it's really minus 9i squared, which is minus 9 times negative 1, which is positive 9. So the first 2 foilings, or the first foiling gives me x squared plus 9. Now I'm going to finish this by doing the multiplications that's left. I'm going to go x squared times x and give me that x cubed, and then x squared times minus 2, which will give me minus 2x squared, and then 9 times x, which will give me positive 9x, and then 9 times minus 2, which will give me minus 18. I claim this is my answer to problem 5. So I did problem 5 and not problem 6, and this is the answer to problem 5. I can check any of these. To check the x equal to 2, I'd plug in 2 for x's and make sure that I get 0. So this is completely optional at this point, but you should be able, for each one of your answers, you should be able to take the numbers that are the zeros and plug them in for x, and you should get 0 out. So the only way my polynomial is right is if when I take each of the 3 zeros and plug them in, that I get 0 out. So if I do 2 cubed minus 2 times 2 squared plus 9 times 2 minus 18. If I get 0, I'm on the right path. If I don't get 0, I've made a mistake. I got 0 there, so I think I'm good. If I wanted to try the f of 3i, I'd have to see that 3i cubed minus 2 times 3i squared plus 9 times 3i minus 18 equals to 0. And again, I could check that on my calculator by going parentheses 3i squared minus 2 parentheses 3i, whoops, it was 3i cubed. Let me just do this again. Parentheses 3 second I up arrow cubed minus 2 parentheses 3 second I squared plus 9 parentheses 3 second I minus 18, and when I hit enter it has to be 0, otherwise I've made a mistake and it's 0. And you could do the same thing for negative 3i as well. So I created my polynomial and I did a little bit of checking. It's probably going to be a little clunky check-in, fade into problem 7 and 8 because this is a cut and fix. Problems 7 and 8 are really not pleasant because I want a 4th degree polynomial, so I need to have 4 zeros. My answer to problem 8, because I'm going to try to do problem 8, my answer has to be f of x equals x to the 4th, and then it's going to have some stuff after the x to the 4th. Unfortunately, I've only given you 2 zeros. I gave you the 0 of x equal to 3i and x equal to 4i. Instinctively, I know that zeros with i's come in pair. The pair for x equal to 3i is going to be x equal to negative 3i. The pair for x equal to 4i is going to be x equal to negative 4i. I'm going to set each one of these equal to 0 and get x minus 3i equal to 0, x plus 3i equal to 0, x minus 4i equal to 0, and x plus 4i equal to 0 just by doing the algebra. And then my function's going to be the product of x minus 3i times x plus 3i times x minus 4i times x plus 4i. When I go to multiply these, I'm going to be clever. I'm going to multiply these two together first, and then those two together second, and then I'm going to do an ugly multiplication. So first I'm going to multiply these two, and I'm going to FOIL them and put that result in my first parentheses. I'm going to multiply this pair second, put that result in my second parentheses. So for this, I'm going to do first outers, inners, and lasts. First are x times x, which is x squared. Outers are x times 3i, which is plus 3xi. Inners are minus 3i times x, which is minus 3ix, or 3xi. And lasts are minus 3i times positive 3i, which is minus 9i squared. The outers and the inners cancel, and the 9i squared turns into 9 times negative 1, or actually minus 9 times negative 1. This parentheses is going to turn into x squared plus 16. Second multiplication, I'm going to do the parentheses by going x times x for the first, which is x squared. X times 4i for the outers are plus 4xi. The inners, minus 4i times x is minus 4xi. And the lasts, minus 4i times 4i is minus 16i squared. Outers and the inners cancel. I'm really left with x squared minus 16i squared, but the I squared is negative 1, and that's going to turn into x squared plus 16. I already see a mistake that I'm going to fix but not re-record. This should be x squared plus 9, because negative 9 times negative 1 is positive 9. I started moving ahead to this parentheses, and I knew what it equaled to, and that's why I wrote that there. So those are the parentheses that I'm going to multiply together to get my answer. I'm going to FOIL these now. First are x squared times x squared, which is x to the 4th. Outers are x squared times 16, which is plus 16x squared. Inners are 9 times x squared, which is plus 9x squared. Lasts are 9 times 16, which is plus 144. For my answer, I guess I'm just going to write it down here for number 8. It's going to be f of x equals x to the 4th. I'm going to combine those and get plus 25x squared plus 144. I don't really care to check. Let me try to check just one of the numbers. I'm going to try to check an easy one, like x equal to 3i. To check x equal to 3i, I'm going to use my calculator and see if 3i to the 4th plus 25 times 3i squared plus 144 equals to 0. If it works, I'm going to assume all my zeros will check. So let me do this real quickly. 3 second I up arrow 4th plus 25 parentheses 3 second I squared plus 144, and I cross my fingers that I see 0, which I do. So I know that 3i is in fact a 0. I can do the same thing with negative 3i, 4i, and negative 4i if I want to check all 4 of them. You don't need to check any of them, but you can check as many as you like. So give 7 a go. I'll move on to 9 and 10, and those are really, really unpleasant. So for 9, it gives you a 0 of 3 plus I. It only gives you 1 0. You need 2 zeros. For 10, I give it a 0 of 4 plus I. I want a second degree polynomial, so I need 2 zeros. So in number 10, my first 0 is x equals 4 plus I. Zeros with i's come in pairs, and you get the pair by changing the sign of the I, not changing the sign of everything. So my zeros for number 10 to create my second degree polynomial are going to be x equal to 4i and x equal to equals 4 minus I. My answer for number 10 is going to have an f of x equal to x squared, and then some junk after the x squared. To figure out what goes after the x squared, I have to multiply 2 factors together. I'm going to set each of the factors equal to 0. The first factor is going to be x minus 4 minus I. And the second factor I'm going to set equal to 0 by minusing 4 and adding I to both sides. And the second parentheses, or the second factor that I'm going to multiply, is x minus 4 plus I. So my function that I'm going to create is going to be the product of x minus 4 minus I times x minus 4 plus I. That's horrible multiplication. There's 9 multiplications that need to be done to do this. I'm going to start off by multiplying x by each of the 3 things in the right parentheses. I'm going to go x times x times minus 4, and x times I for taking x and multiplying it by each thing in the right parentheses. That's going to give me x squared minus 4x plus xi, or plus ix. I'm going to write plus xi with a 1 in front of it. That's 3 of my 9 multiplications. The next multiplications I need to do are with the negative 4 multiplied by each of the things in the right parentheses. I'm going to go negative 4 times x, negative 4 times negative 4, and negative 4 times I. Negative 4 times x is going to be a minus 4x. I'm going to write it right under the other minus 4x to make it easier to do. Minus 4 times minus 4 is plus 16. And minus 4 times I is minus 4i. So I've done everything with the x, everything with the minus 4. Now I need to do everything with the minus I. I need to go minus I times x, minus I times minus 4, and minus I times I. minus I times x is going to be minus 1xi. I'm going to write it right under that minus 1xi for it to cancel. The minus I times minus 4 is going to be plus 4i. I'm going to write it under that 4i for it to cancel. And the minus I times minus I is minus I squared. It's actually minus I squared. This is really minus 1 times I, if I want to think of it like that. The minus I is minus 1i. This comes out to minus 1 times I squared, which is minus 1 times minus 1, which is plus 1. And I'm going to write that under the 16. So this whole polynomial is going to have an x squared, minus 4x is minus 8x. The minus and positive 1xi canceled. 16 plus 1 is 17. And the minus 4i and positive 4i cancel. So it's not my best explanation of this problem ever. I claim that this is my answer to number 10. Let me check, and I'm just going to check one of the two zeros. I'm going to put 4 plus I in for x and see if 4 plus I squared, putting it 4 plus I in for that x, minus 8 times 4 plus I plus 17 equals to 0. If it works, I'm going to say I'm right and not do any more. So I'm going to go parentheses 4 plus second I squared minus 8 parentheses 4 plus second and decimal for the I plus 17. If I had equals and get 0, I know that that is good. I could do the same thing for the 4 minus I. So give number 9 a try and see what you can do with it. 11 and 12 are the same problems. I don't generally put problems like this on the test, so I'm not going to do 11 and 12. If you take a makeup test for the chapter, that I might put these ugly problems on. So if you're going to take a makeup test, make sure you learn how to do number 11. If you can't figure it out, I'll show you. Come to my office and I'll show you how to do it. The rest of the section is a little bit icky. It gives me a polynomial and it gives me a 0 with an I, and we're asked to find the remaining zeros. So if I look at problem 14 gives me the function f of x equals x cubed plus 3x squared plus 25x plus 75, and it says x equals 5i is a 0. Because this is a third degree polynomial, I know it has 3 zeros. So for my answer to problem 14, I'm going to say the zeros of my function are, and there need to be 3 of them because a third degree polynomial has 3 zeros. I was told that 5i was a 0, so that's one of the 3. I know that zeros with i's come in pairs, so negative 5i must also be a 0. Unfortunately, I don't know what the third 0 is, and I'm going to need to use double synthetic division to get it. So to find out the third answer to problem 16, I'm going to do synthetic division. And what I'm going to do for my synthetic division is I'm going to take the coefficients of the function 1, 3, 25, and 75, write them above a line, and to the left of that line, I'm going to write the 0 that was given, which is 5i. Now I'm going to do synthetic divisions with i's, which means I'm going to use the heck out of my calculator. I'm going to bring down the 1, and then I'm going to multiply 5i times 1, and 5i times 1 is 5i. And then I'm going to combine these and get 3 plus 5i. Now I need to multiply 5i times 3 plus 5i. Do that on my calculator. So that multiplication of 5 second I times 3 plus 5 second I is going to equal to negative 25 plus 15i. So under the 25, I'm going to write negative 25 plus 15i. The 25s are going to cancel. I'm going to bring the 15i down. And now I'm going to go 5i times 15i. So 5 second I, 5 second I times 15 second I and I get negative 75. So this multiplication of 5i times 15i gives me minus 75. That gives me a remainder of 0. Done with the first level of my synthetic division. Now I'm going to do a synthetic division with the numbers other than the remainder that are under the bar with the second 0 of negative 5i. I'm going to bring down the 1. Then I'm going to go negative 1. I'm going to go negative 5i times 1 is negative 5i. I'm going to combine these. The 5i's are going to cancel. I'm going to be left with a 3. Now I'm going to go 5i times negative 5i times 3 and get negative 15i. And I get a remainder of 0. I claim that this is going to help me get that third 0 that I'm missing. The initial polynomial started off at a third degree. The first synthetic division would drop the answer down to a second degree. The second synthetic division is going to drop it to a first degree. So when I write the polynomial that is implied by this, the 0 is the remainder. The exponent I start with is 2 less than the initial exponent. The initial exponent was 3. I need to start with an x to the first power. The polynomial that's implied by this synthetic division is x plus 3. I'm going to set that equal to 0 to get my third 0. So the answer to the second synthetic division is x plus 3, remainder of 0. I'm going to set that answer equal to 0, and I'm going to get my third 0 to this polynomial. I'm done with problem 14. If I want to check to see if my answer is right, that 5i, negative 5i, and negative 3 are zeros, I can take any one of those and plug them into the original function. So if I wanted to see if negative 5i was a 0, I can go to the original function and change the x to negative 5i. I can go negative 5i cubed plus 3 times negative 5i squared plus 25 times 5 negative 5i, 25 times negative 5i plus 75. Negative 5i is only a 0 is if after I enter that in for the x's, when I hit equals I get 0. Similarly, I can check the negative 3 by going parentheses negative 3 up arrow cubed plus 3 parentheses negative 3 squared plus 25 parentheses negative 3 plus 75, and I should get 0 when I hit enter. If I didn't, my answer was wrong, but because I got 0, I know my answer was right. So do the same thing for 13, and I will move on and do 15 and 16, and just to be nice, I'll do your problem 15, just so you won't have to do so many of these by hand. So for problem 15, my answer, I'm trying to find the 3 zeros of this polynomial. So my answer for problem 15, the zeros are going to be 3i, because that's given, negative 3i, because i's come in pairs, and then the third 0 I need to get using double synthetic division. So I'm going to take my problem 15 and write down its coefficients, 1, negative 4, 9, and negative 36. I'm going to take the 0 that I'm given and do synthetic division with it. I bring down the 1. I multiply the 3i and the 1 and get 3i. I combine these and get negative 4 plus 3i. Now I multiply 3i times negative 4 plus 3i on my calculator. So I'm going to go 3 second I times negative 4 plus 3 second I, and I'm going to get negative 9 plus 12i, negative 9 minus 12i, that I'm going to write right under this 9. The 9's are going to cancel, and I'm going to be left with the 12i. And then I'm going to multiply 3i times 12i on my calculator, 3 second I times 12 second I. I get minus 36. That's troublesome. This should be minus 12i down here. This minus in front of the 12 should have stayed, and I should have multiplied 3 second I times negative 12 second I and get positive 36. That's going to give me a remainder of 0. I've used that 0. Now I'm going to take the 1 minus 4 plus 3i and the minus 12i, ignore the remainder, and do synthetic division with the negative 3i. I'm going to bring down the 1, and I'm going to go negative 3i times 1 is negative 3i. I'm going to combine these. The 3i's are going to cancel. I'm going to have a negative 4. And then I'm going to multiply negative 3i times negative 4. So negative 3 second I times negative 4. I get positive 12i, which I'm going to write under the 12i. I'll get a remainder of 0. Done with my double synthetic division, I'm going to create a polynomial from this. And because the initial exponent was 3, and I've done double synthetic division, I need to lower the exponent by 2 from 3 to 1. So this is going to be 1x minus 4 with remainder of 0. I'm going to set this x minus 4, the result of the double synthetic division, equal to 0 and solve for x. And I'll get x equal to 4 for my third 0. So in my answer to problem 15, the zeros in problem 15 are going to be x equal to 3i, negative 3i, and x equal to 4. You can check these real quickly. Let me check the 4 by just plugging 4 in for each one of those x's, going parentheses 4 up arrow cubed minus 4 parentheses 4 squared plus 9 times 4 minus 36. The only way that this 4 is correct is if when I hit enter I get 0. And it does, so I know that's correct. The negative 3i's, I probably really don't have to check, because if the 3i is a 0, its conjugate pair or its opposite is also a 0. All right, so that'll be the end of section 5.3, and we just need to move on.